Okay, so in this video I will continue my applications of Silo theorems and problems based on Silo theorems, but before that let me do actually a couple of small results that do not use Silo theorem, but they are useful applications of group actions. So, let us say this is a problem I want to solve today. Let us say G is a group and P is a prime number, and let us say G has order p power n, let us say E. Okay. In other words, G order of G is a power of P, and let us say E is at least 1. Okay. So, show that the center of G is non-trivial. Okay. So, I will explain what this means. So, recall the center of G, it is denoted by ZG, is all elements of G which commute with other elements, all other elements. So, the problem is asking us to show it is non-trivial. So, we want to show order of ZG is at least 2. Okay. So, remember this need not be the case. If you, I will only say this, you can check this on your own. If G is S3 for example, the symmetric group of on 3 letters, the center is trivial. Of course, the symmetric group does not have this property that its order is a prime power. So, if you have this, prime power groups have a non-trivial order. So, for this we consider the action of G on itself by conjugation. Okay. So, this is something we have seen before. So, in particular we look at class equation. What is a class equation? It says that cardinality of order of G, which I am assuming is E, p power E, is the sum of conjugacy classes, orders of conjugacy classes. But remember, one conjugacy class is just E, this is the orbit of E. Conjugacy classes are orbits of elements under conjugation action. So, the class equation looks like p power E is equal to 1 plus C2 plus C3 plus Ck. Now, we further apply group actions. So, what does counting formula say? Counting formula says order of G is stabilizer of some element times orbit of that element. Again, this is p power E. So, we can certainly say that the size of a conjugacy class or size of an element, orbit of an element, divides p power E. But what are the numbers that divide p power E? So, orbit of G must have size p power some I for I equal to, it can be 0 of course, to up to E. Now, let us go back to the conjugacy class equation. You have 1 plus C2 C3 plus Ck. Using the counting formula, I can say that each of these is a power of P, even one is a power of P. So, this is some P power, let us say A2, P power A3, P power Ak, right. Suppose A2 is positive, A3 is positive, Ak is positive, suppose they are all positive, then Pe will be 1 plus Pa2 plus Pak, and this whole thing is divisible by, right, because if they are all positive, that means P divides 1, because P divides P power E, P divides this sum. So, P divides the difference, which is 1, but this is absurd. But where did we go wrong? We went wrong in assuming that all the AIs are positive. So, some AI is equal to 0. So, say A2 is 0. That means what? C2 has order 1. But what is C2? So, A2 remember is the order of C2 is p power A2, A2 is 0. So, order of C2 is 1. This implies C2, which is the conjugacy class or orbit of some element G, has only one element. But what is orbit of G? Is all elements like this. But of course, orbit definitely contains G, but that means A G A inverse is G for all A in G. That means A G equals G A for all A in G. That means A belongs to the center. But of course, and note that C A must be sorry, this is not A that I can conclude is in center. A is varying, so I can conclude G is in the center. And remember, G is different from E, because I am taking the second thing that appears in the class equation. These are distinct orbits. E already is taken care of when we wrote 1. So, C2 being the order of G, and G must be different from E. So, we have produced an element G in the center, which is different from E. So, that concludes that the center is non-trivial. Okay. So, that proves the solves the problem. So, if you have a group whose order is prime power, such groups are called P groups. We have shown that the center is non-trivial. So, P groups have non-trivial center. Now, I am going to consider a special kind of P group. Suppose G has order P or P squared, where P is prime, then G is abelian. So, it is not true that P groups are abelian, all we know is that their center is non-trivial. So, there are non-identity elements in the center, but if it is either P or P squared, the center is everything. In other words, the group is abelian. So, if G is P, then G is isomorphic to G is actually a cyclic group, implies G is abelian, right. There is nothing new here, we have seen this before. So, assume order of G is P squared. So, we want to show G is abelian. Equivalently, we want to show, note that by the previous problem we know that the center is non-trivial. So, center must contain something bigger than center must be bigger than just the identity, but now we want to show that it is all of G. What are the possibilities for the center? So, center is a subgroup which is between E and G. By the previous problem, it is not equal to E. So, it is either G or it is strictly between. So, suppose if possible the center is not equal to G. So, you should think for a minute, if it is not clear to you, why the center being all of G implies G is abelian. This is just the definition of what a center is. So, suppose the center is not equal to G. So, choose x in G, x not in the center, right. If x is not in the center, if center is not all of G, there must be something that is not in the center. Let us consider the conjugacy class of x, that means C of x, which is the set of elements G x G inverse. as G varies. Okay. So, this is actually, sorry, this is the centralizer, for this is called the centralizer of a recall. And it is a subgroup, and I will let you do this easily. Check that this is a subgroup of G, because if identity certainly has this property, if two things have that property, their product has this property, and if something has this property, inverse also has this property. Now, this is easy check. It is also easy to check that the center will always be contained in the centralizer, because center, remember, is all elements which commute with everything. So, if something commutes with sorry, so this is actually, I made a mistake here. So, let us so actually let me erase all this. I got confused. I am not looking at the conjugacy class, I am looking at the centralizer. Consider the centralizer of X. I will call it Cx. This is by definition all G in G such that Gx G inverse is X. Okay. So, this is a subgroup of G, and this contains the center. That is what I want to say. Why is this? This is all group elements which commute with right. So, these are the group elements which commute with everything. Cx is a group elements which commute with X. So, center contains Cx. So, what do we have? We have E, we have Zg, we have Cx, we have G. The reason we need P squared is this. So, this is order 1, this we are assuming is order P, because it is strictly between G and Zg, and this is P squared, and Cx, remember, Cx contains X, because X certainly has this property, X inverse is X. So, Zg and Zg does not contain X, that is our assumption. So, this implies Zg is contained, but not equal to centralizer. So, this must be P squared. That means, so Cx is equal to G, all of G itself. That means, Gx equals Xg for all X, for all G, right. That is the centralizer. It is all elements which have Gx equal to Xg, but that is all of G. So, Gx equal to Xg for all G, but this in turn means that X is in the center. This is a contradiction, right. This is a contradiction. Because we chose if possible we chose X to be not in Zg. So, this shows that any group of order P squared or any group of order P is abelian. So, now using these two facts which do not require Silo theorems at all, these two problems, I am going to do a third problem which does use Silo theorem. So, let us say G is a finite group and P divides order of G, and as always P is a prime number. Okay. So, in fact, suppose that P power E divides order of G, then G has a subgroup of order P power E. Okay. So, this is the problem. So, this looks very much like first Silo theorem, but with some difference. The first Silo theorem is the key statement that we will use, but we have to do some more work, because the first Silo theorem says that you take the largest power of P that divides the order of G, then there is a subgroup of that order. Here I am not assuming that P is the largest power. So, how do we do this? so first I can, so first without loss of generality we say, we claim that without loss of generality we can assume G is a P group, that is order of G is a power of n, power of P. Why is this? Meaning why can we assume this? So, write G as some P power, I think maybe I should not use E here. Let us say, suppose G is a finite group and P power I divides G, then G has a subgroup of order P power I, and here I can assume that I claim this. So, write like this, like we do in the Silo theorem. So, P does not divide M. Silo 1 implies G has a subgroup order P power E, say H. Say H is the subgroup of G of order P power E. Now, if I is less than E, if we show take I less than or equal to E, if we show H as a subgroup of order I, then G also has a subgroup, right, the same subgroup which is a subgroup of H is also a subgroup of order I for G also. So, it is enough to show that H contains a subgroup of order P power I. So, we can restrict our attention and this, in order to make this assumption we need the Silo theorem, in the rest of the proof we do not need. So, Silo theorem is needed for this reason. So, assume now that G is, so we can from now on assume order of G is P power E and I is less than E. We want to show G has a subgroup of order P power I. Okay. Just to quickly recap why we can make this assumption, if G need not be a P group, but it will have its order will decompose like this. Silo 1 says that G has a subgroup of order P power E, and if you prove the problem for that subgroup, we have solved the problem for the given subgroup, given group G. So, we might as well assume that G is a group of order P power E. Now, by a corollary of first Silo theorem, we can assume that no, not corollary of the first Silo theorem. By the first problem of this video, the center of the group is non-trivial, right. We have shown that a P group has non-trivial center. So, take so it has non-identity elements. So, I can always choose an element, let us call this X of the center such that order of X is P, and in order to do this I use the corollary to the first Silo theorem. Remember, there is an element of the center which is not identity. Order of the center is also a power of P, in other words the center is also a P group, because the order of the center divides P power E. So, order of the center is also a power of P. So, an element will have order a power of P. So, by taking a suitable power of it, we can assume that it has order X. So, look at corollary to Silo 1 that we have done in that video for producing such an X. And now, let H be the subgroup So, I am starting with a new notation here, whatever I called earlier H is gone now. So, now G is a subgroup, a group of order p power e, and H be the subgroup generated by X. So, H is the subgroup generated by X. So, order of H is P of course, because order of X is P. More than that, H is in fact normal in G. Why is that? Because X is a central element, X is in the center. So, how do you show something is normal? Take an arbitrary group element, an arbitrary ring element, it will be some x power m or x power n and multiply by G inverse. But remember, X is in the center, right? We have chosen an element X of the center. So, x power n also is in the center. So, x power n G inverse, this is x power n, this is of course in H. So, H is normal in G. So, in particular we can consider the quotient group right. If you have a normal subgroup of a group, you can consider the quotient group, and let us look at the map from G to G mod H, the natural map. So, small g going to the coset G H. What is the cardinality of G mod H, order of G mod H? By the counting formula, this is the ratio. So, this is p power e, this is p, so this is p power e minus 1. Okay. Now, by induction, so I am going to basically solve this problem by induction. So, we use induction. Order of G mod H is p power e minus 1, which is less than p power e. So, we can assume by induction that G mod H has a subgroup say k prime, such that the order of k prime is p power I minus 1. So, I am going to construct my goal is to construct a subgroup of order p power I for G. I am going to use induction hypothesis to suppose that G mod H, which is a group of order less than p power e, has a group of order subgroup of order p power I minus 1. So, what is the picture? We have G mod H, k prime, which is a subgroup. This has order p power I minus 1, this has order p power e minus 1, this has order p power e. How do I get? So, this is the picture. How do I get the k that we want, the group of order subgroup of order p power I? Okay. So, naturally your guess would be I take phi inverse k prime, call that k. So, let k be phi inverse k prime. It is an easy exercise that I may have discussed when I talked about homomorphisms. Inverse image of a subgroup is a subgroup. So, k is a subgroup of G. We claim that k is the desired subgroup. We claim that k has order p power I. So, remember our goal is to construct, given that G is a G has order p power e and I is less than or equal to e, we want to show G has a group of subgroup of order p power I. We use induction and go to a smaller group, which is G mod H, and apply induction to that to guarantee that there is a k prime for which is a subgroup of G mod H, which has order p power I minus 1, and I am simply taking the inverse image, k will be the inverse image. So, it is a subgroup, that is trivial. We want to show that in fact its order is p power I. So, why is that? This is very easy now. So, remember we have G to G mod H, k is here and k to k prime we have a map, because k, this is phi restricted to k. And because k is the inverse image of k prime, K maps to K prime. So, what is the kernel of this map? Remember, K will, what is the kernel of phi first? Kernel of phi is of course H, right. Kernel is the inverse image of identity element. So, K prime contains the identity element. So, its inverse image will contain all of the kernel. So, K contains H, we have this also. So, kernel of phi restricted to K, I claim, is also H, because how can something go to 0 here or the identity element here? If it goes to identity element here, it already goes to identity element here. So, it is in H. So, if something is in H, it is already in K. So, kernel of this is phi mod K of is H, and of course, phi restricted to K is also onto, it is onto, right, because phi itself is onto. So, this is also onto. So, forget this now, focus your attention on this map and apply counting formula. It says that, or the first isomorphism theorem really. First isomorphism theorem says that K mod kernel of this map, which I am denoting by phi restricted to K, is isomorphic to K prime, but that is same as, because kernel is H. This implies that now the counting formula says that order of K by order of H is order of K prime, which remember is p power I minus 1. So, order of K is order of p power I minus 1 times order of H, but order of H is p. Okay. So, thus we have produced a subgroup K of G of order p power I. Okay. Remember, this was the problem. Problem was to show that if you have a group G such that p power I divides the order of G, then there is a subgroup of order p power I. So, now first using the first Silo theorem, we have reduced to the case that G has order p power E. That was the crucial restriction, and that needed Silo's first theorem. Then we used the fact that for such p groups the center is non-trivial, and get hold of this X, which made all the proof work. And then we go to G mod the subgroup generated by X, use induction to show that that has the right subgroup, and we take the inverse image, and then a quick application of first isomorphism theorem, and counting lemma says that, counting formula says that the inverse image has the desired property. So, this proves the problem, and this completes the video and the course. I wanted to cover the standard things that are done in a group theory course. So, we have done Lagrange's theorem, cosets, quotient groups, Cauchy's theorem, group actions, which is the most important topic here, and using that we have done the Silo theorems. So, this is the material that is covered in any standard course in group theory, and if you understand this course fully, then you know the group theory that is expected in a BSc or a MSc course. Thank you.